Welcome to the video lecture on inverse functions. We're going to talk about how to decide whether or not a function has an inverse, and if so, what's its formula. So let's first talk about some relations. A relation is just a general correspondence between any x's and any y's. And you can represent a relation in many different formats. So this first problem gives us a list of ordered pairs as our relation. And let's talk about how you can write that same relation using a mapping and using a graph. So a mapping diagram consists of two great big circles, and it just is a nice physical way of representing what's going on between our points. So in this first circle are going to be our x values, in the second circle are our y values, and we're going to show arrows that connect the x value with its corresponding y value. So in this first ordered pair we have -2 being sent to 1, so that's how we're going to show it in a mapping. Then we have 5 being sent to 4, 3 being sent to 1, and since I've already used 1 in my outputs over here, I'm going to continue to use it again and just draw my arrow up like that, and then 6 gets mapped to 2. So that's what a mapping would look like. Now in a graph, since we have ordered pairs here, these are just going to be represented as dots. So -2, 1, 5, 4, 3, 1, and 6, 2. So first of all, here's our relation. Is it a function? How do you tell if something is a function or not? The definition of something being a function is that every x value gets sent to a unique y value. So you can only use unique x's. Each x can only be used once. And that's really easy to see from a mapping, because you can see that every x got sent to exactly one y, and that's what we want for a function. So yes, this is a function. Another way to tell if something is a function is to use that vertical line test. And if you imagine drawing a vertical line through our graph here, it's only going to intersect those points exactly once, so it would pass the vertical line test as well. Now what we're going to do is we're going to reverse this correspondence to create what we call an inverse. So to create our inverse as a list, all we have to do is swap our x's and our y's. We're going to reverse it. So we would have the set of points, and instead of having -2 going to 1, now it's going to be 1 going to -2. And 5, 4 becomes 4, 5, 3, 1 becomes 1, 3, and 6, 2 becomes 2, 6. Now let's show that as a mapping. So using my two circles again, 1 gets sent to -2, 4 gets sent to 5, 1 gets sent to 3, but I already have a 1 in my input circle, so I'm going to continue to use it again, but just draw a second arrow going to 3, and then 2 gets sent to 6. If we write these as dots or points on our graph, this would be 1, -2, 4, 5, 1, 3, and 2, 6. Now if you look at these mappings and graphs here, does this represent another function? And hopefully you can see that the answer should be no. If you look at your mapping, this input of 1 got sent to two different y values. We have that double arrow showing up. You could also see it in the fact that we used 1 twice in our list, and you could also see it in the fact that if you were to visualize a vertical line, it's going to intersect at this dot as well as this dot. So our vertical line would intersect twice, so that means it fails the vertical line test. So that means we do not have another function. And that's something that we're going to be aiming to do in this lecture. We want to find a way of knowing whether or not, if we were to reverse the correspondence, we would end up with an inverse function or not. And if so, what's its formula going to be? So let's take a look at another example. This time we have a formula given to us, x squared. And what we want to do here is draw a sample mapping. We can't actually draw the entire mapping because this allows for all possible x's, which is an infinite number of values. So what we're going to do is just create a sample so that we can get a feel for what this would look like. And for a sample mapping, it would be just like if you were making a table of values. I might choose my x's to be -2, -1, 0, 1, and 2, and then see where those plot to. And this is the squaring function, so -2 squared becomes 4, -1 squared becomes 1, 0 squared becomes 0, 1 squared goes to 1, and I'm going to draw my arrow up, and 2 squared goes back to this 4 again. So if I plot these points, -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4, and we get that nice parabola shape that we're used to, with the vertex at the origin and a pattern of over 1, up 1, over 1, up 1 on either side, over 1, up 3 on either side. Is this a function? Yes, it passes that vertical line test. So now let's reverse the correspondence. So to do that in our mapping, think about this point -2 being sent to 4. We're going to reverse that. So 4 is going to be sent back to -2. The second point we had -1 going to 1, so now we're going to have 1 going back to -1. We had 0 going to 0, so if we reverse that, 0 still goes to 0. Here we had 1 going to 1, so now we're going to have 1 going back to 1 again. We already used 1 over here, and now it's going to go to 1 on the right side. And here we had 2 going to 4, so now we're going to have 4 being sent back to 2. And I already used 4 once, I'm going to use it again to send it back to 2. If we plot these points, then we'd have 4, -2, 4, +2, 1, -1, and 1, +1, and 0, 0. And what you'll end up with this graph, it looks like a parabola, but it's a parabola on its side. So when you reverse this squaring function, you end up getting sort of a sideways parabola. Is this a function? Well, you can see that if I were to draw vertical lines through this sideways parabola, it's going to fail that vertical line test. So no, this is not a function, because it fails that vertical line test. You could also see it from the mapping, because I have those double arrows coming from the 4 and the double arrows coming from the 1 as well. Now, is there a way to change this problem slightly so that we do allow there to be a function as a result of reversing our correspondence? And there is a way to do that. So instead of allowing the function f, which was x squared, to go through all x's and be this entire parabola on both sides, what we could do instead is restrict the domain, and I'm going to show you how to do this a little bit later. We could restrict the domain so that instead of using the entire parabola, maybe we would just use half of it. And then if we reverse that correspondence, then the inverse graph would look like a sideways parabola, but we wouldn't be using both sides anymore. If we're using the positive x's here, we would use the upper half of the parabola over here. And that causes us to have a piece of a graph that will pass that vertical line test and will be a function. So by restricting the domain, we are able to end up with an inverse function, which passes that vertical line test. So we're going to see how to do this a little bit later on, but if you start off with a function that normally when you reverse it does not give you a function, there are ways to restrict the domain so that you do end up with an inverse function. Now let's talk a little bit about some vocabulary words. In order for a relation to be a function, the definition of our function is that the arguments, or the x values, or the inputs, whatever you want to call them, cannot have more than one image, or y value or output. In other words, no two ordered pairs can have the same first element. And this would be the same as saying that you don't want to have any x repeats. So no x's can repeat. They have to be unique. We don't want to see those double arrows coming out of the x's, sending those x's to two different y's. In order for a function to be reversible and still yield a function, then the images or the y values cannot have more than one argument or x value. So in other words, no two ordered pairs can have the same second element. In other words, no y's can repeat. If that happens, so that you have no y's that repeat, then such a function is called one-to-one. So here's the formal definition of being one-to-one. We say that a function f of x is one-to-one if and only if, when the x's are not equal, then the y's should not be equal. Or this is the same thing as saying that the function is one-to-one if and only if the y's do equal each other, then the x's must have equal each other. So what we want to make sure of to be one-to-one is that we have unique x's and unique y's. The x's should not repeat to force it to be a function, and the y's should not repeat to force it to be one-to-one. So here are three different mappings that are going to hopefully help you visualize a little bit more about what we're talking about. So if we look at this first mapping, is this mapping a function? Yes, because each x is unique and is being sent to exactly one y. We didn't have any x's being repeated here. We didn't have any of those double arrows coming out. So we have unique x's. That makes this a function. Now if we were to reverse this, would we end up with a function back again? And the answer is yes, because we also have unique y's as well. And that means the fact that we have unique x's and unique y's, that means this is a one-to-one function. So that if we were to flip these back, we would get a nice function in reverse. If we take a look at this example here, is this a function? Yes, because each x is unique. I don't have any of those double arrows. But are the y's unique? And in this case, no, because y1 is getting used twice. So the x's are unique, but the y's are not. So that means this is not a one-to-one function, which means that if you were to reverse this correspondence back, you could see right here that y1 would get sent to x1 and y1 would get sent to x2, which makes it not be a function. And that's what being one-to-one would guarantee, and that's why it's not one-to-one. Okay, let's look at one more example. Is this mapping an example of a function to begin with? And the answer there is no, it's not a function because the x's are not unique. We get that x sub 1 being used twice. So if we were to reverse this, we're not going to get something good back again, but it's not a function in the first place, so it's not even going to be one-to-one because it's not a function. Alright, let's practice this by looking at some functions and determining whether or not they're one-to-one. So if we look at this first one, this one doesn't give us f as a rule, it gives us just a list of ordered pairs. So if we want to determine whether or not this is one-to-one, first let's decide whether or not it's a function. So to figure out if it's a function, we're going to look at these x's and make sure that they are all unique, which they are. So we have unique x's, which implies that f is a function. And then to determine if it's one-to-one, we would look at the y's and see if they were unique. So if we look at our y's, we have 3, 2, and 3, which means we do not have unique y's. We have repeated y's. And if you have repeated y's, then that means you are not one-to-one. So this is not a one-to-one function, which means that if you were to reverse this correspondence, you would not get back a function, because 3 would get mapped to 1, but 3 would also get mapped to -1. Alright, let's try it on the next example. So here's the function h. Is it a function to begin with? Yes, because we have -2, 2, and 1, so we have unique x's. Do we have unique y's? 4, 6, and 1? Yes, we do. So we have unique x's and y's, so therefore it is one-to-one, and therefore if I were to swap these x's and y's, I would get a function back. Now this bottom example is a little bit trickier to do because we're not given ordered pairs, we're given a formula for this, g of x. So in order to determine whether or not it's one-to-one, we're going to have to be a little bit more careful. So what I might suggest here is considering a graph. And this function right here is quadratic because of that x squared. So we could make a graph of what this parabola is going to look like. And I know it's a parabola because of the x squared, and I know it's a parabola that points up because that x squared term is positive. Now if you really wanted to be super careful, you could go through all the work of finding the vertex using minus b over 2a and doing all of that. What I'm going to show you is just a more general approach to graphing this. We get a little bit lucky here because this particular quadratic function factors. So let's take a look at the factors. We could have x and x, 4 and 1. If I make the 4 minus and the 1 plus, then I'm going to get a negative 3 in the middle. The fact that this factors means that it would be very easy to find out where this quadratic function equals to 0. It's going to equal 0 at 4 and at negative 1. And that means those are the zeros on the x-axis. So that means this is our x-intercepts. So if I were to draw a graph, I know that this graph hits 0 at x equals to 4 and x equals to negative 1. So I know a couple of intercepts. You could even graph the y-intercept. We know that when x is 0, these two terms would go to 0, leaving me with a y value of negative 4. So you could also plot that as well. And as I said before, if you really wanted to get fancy, you could find the vertex. But all I want to do is just draw the general shape of this graph. And we know it's a parabola that points up. So this is going to have to look like something like this. So here's the graph. That is a function because it would pass the vertical line test. But the question is it one-to-one? And to answer that, you have to think about, does it use unique y's? So I want you to visualize this horizontal line going across. What is true about these 2 points that intersect on that horizontal line? Say that this horizontal line is at a height of 4, and I'm just making up a number here. What we would know is that this coordinate, this point right here, has a y value of 4. And this point over here also has a y value of 4. Now they have different x's, but they share the same y. So these would be an example of 2 points that do not have unique y's, which means it is not a one-to-one function. So this kind of leads us into our next topic, which is a graphical way of deciding whether or not you are one-to-one. Remember, we have this vertical line test, which we use to determine whether or not we have a function. Well, now we have the horizontal line test. So if you imagine drawing horizontal lines through your graph, if those horizontal lines intersect in more than one point, then that's going to be proof that you do not have a one-to-one function. So here's what the horizontal line test says. A horizontal line test says that if every horizontal line intersects your graph in at most one point, then it is a one-to-one function. And that implies that if it intersects in more than one point, then you do not have a one-to-one function. So it's a nice, easy visual test to use to see if something is one-to-one or not. Okay, let's talk a little bit about notation. When we talk about a function undoing another function, that's what we're going to call our inverse. And the notation that we're going to use for an inverse function is this little -1 exponent. So f of -1 of x really means f inverse of x. So this represents the notation that we're going to use whenever we are referring to the inverse of f. Keep in mind, just as a side note here, that a lot of times in mathematics, when we see -1 exponents, usually that implies to take a reciprocal or flip something over. And that's different than what we're doing here. So in order to really flip something over, it would have to look something like this. The entire function raised to a -1 power, and then that does mean flipping over f of x. That's not what this is doing. So whenever you see that little -1 sort of squeezed in between the f and the x, that always is implying inverse, and it doesn't mean reciprocal. In order to have an inverse, your function f has to be 1-to-1. That's why being able to determine if something is 1-to-1 or not is so important. How do you find the inverse if you know that it has one? Well, you're going to swap x's and y's, because that's what an inverse does. So if a function f has the point x comma y on it, then the inverse function, f inverse, is going to have the point y comma x. You're just going to swap your x's and your y's. Now, because domain is x's and range is y's, we also get to swap the domain and the range. So in other words, the domain of f becomes the range, whoops, let me do it this way, becomes the range of f inverse, and the range of f becomes the domain of f inverse, because domain is just all your x's, and those become all your y's, and the range is all your y's, so those become all your x's. So domains and ranges get swapped as well. Now, one characteristic or condition that has to be maintained in order for two functions to be inverses is the following statement right here. F composed with f inverse of x has to equal x, and f inverse composed with f of x has to equal x as well. What does that really mean? Well, remember, composition means you do one function followed by another one. So on this one, this first example here, we're starting with an input of x. We're going to apply f inverse to it, which will change it a little bit, and then f is going to undo everything that f inverse just did and give you back the x that you started with. And this second statement does exactly the same thing, but it just does it in the other order. So if you start with x, f is going to do something to that x. F inverse will undo everything that f just did and give you back your original x. So these two statements basically just mean that f and f inverse undo each other. So occasionally, you will be asked to prove that two functions are inverses of each other. If you look at these two functions, f and g, it wouldn't be very obvious that they are inverses of each other. So what we would want to show is that when I compose these two functions together, I do get back x. And formally, this is what you would have to do to prove that these are inverses of each other. You would have to show that the function f composed with its inverse gives you back x, and then you also have to show it in the other order. You have to do it both ways. So if you start with f inverse and compose it with f, you should get back x as well. Now, what I have written down here as f inverse is really what I have up here as g of x. So I'm just going to relabel this so that we can kind of keep the notation consistent with our condition up above. So here's how you would show this. You would need to take f composed with f inverse. So let's do that. And remember, for a composition, you start with the inner function. What's the rule for f inverse of x? Well, it's this big fraction over here. So we're going to take 2x plus 1 over 3x minus 1, and that now becomes the input into f's rule. Now, f's rule says take whatever your input is, add 1, and then divide by 3 times your input minus 2. So let's do that. This time our input is this great big fraction. So we're going to take our input, this big fraction, and we're going to add 1. And then on the bottom, we're going to do 3 times our input, this big fraction, and then we're going to subtract 2. So it looks really messy, and now it's going to be our job to try to clean this up. So to clean it up, because we have fractions within fractions, what we're going to want to do is look at our denominators. And I have a 3x minus 1 on the top and on the bottom. So what I'm going to do to clean it up is multiply both the top and the bottom by this common denominator. Now when I take this first fraction times that common denominator, the entire 3x minus 1 terms cancel out, and all we're left with is this numerator 2x plus 1. So we just multiplied this first term in front of the plus sign times our common denominator. Now we have to remember to multiply the 1 times that common denominator as well, so that's just going to leave it as 3x minus 1. Now let's do the same thing in the denominator. When I multiply this whole big term times 3x minus 1, the 3x minus 1's cancel, and I'm left with this 3, and then parentheses 2x plus 1. Then I also have to multiply the negative 2 times the common denominator, and initially here I'm just going to write that minus 2 and then in parentheses the common denominator. In the next step I'll go ahead and distribute. So let's go ahead and clean up the numerator a little bit. You can see that the 1's are going to cancel, and 2x plus 3x is 5x. On the bottom, when I distribute, I get 6x plus 3 minus 6x plus 2. So the 6x's cancel, and we get 5x over 5. 5's cancel, and hey, we got our x back. So no matter what input we started with, when we compose f with f inverse, we always get that same x right back again. So that's what we were trying to prove. Now unfortunately, we're not done because we have to do that all over again, but in the opposite order. So instead of starting with f inverse first, now we want to start with just f of x first. So let's take f inverse composed with f. So what's the rule for f of x? F of x is this big fraction over here, x plus 1 over 3x minus 2, and now we're going to input that into f inverse. So we're going to go to the rule for f inverse. 2 times the input plus 1 over 3 times the input minus 1. So we need to do 2 times this whole input, this whole fraction, plus 1, all over 3 times the input, or 3 times this whole big fraction, minus 1. And just as before, it's very messy, so the easiest way to clean it up is to multiply by my two denominators, my 3x minus 2's, on the top and the bottom. When I multiply this first fraction across, the 3x minus 2's cancel, and I'm left with my 2 and my x plus 1. And then I need to multiply my 1 times that 3x minus 2, so it's going to stay 3x minus 2. In the denominator, when I multiply my fraction across, the 3x minus 2's cancel, and I'm left with my 3 and my x plus 1. And then on the bottom, I'm going to have negative 1 times that 3x minus 2. So again, I'm just going to use parentheses for now, and I'll distribute in the next step. So on top, we get 2x plus 2 plus 3x minus 2. And on the bottom, we get 3x plus 3 minus 3x plus 2. The 2's cancel on top, giving me 5x. The 3x's cancel on the bottom, giving me 5. The 5 cancels, giving me x. So it's pretty slick how it works out each time, that no matter what order we started in, we are always going to end up with that original input x back again. Now in that last example, we were told our function and its inverse, and then we were just verifying that we had the correct inverse. What we're going to focus on next is how you would actually find the formula for the inverse functions, and sometimes it's not very obvious what it should be. So here are the 4 steps that we're going to go through. First, you have to show that it's one-to-one. And once you know that a function is one-to-one, so that it has an inverse, you're going to start by replacing f of x with y. Then we're going to swap our x's and our y's. Then we're going to solve for y in terms of x. And in the last step, we're just going to change our notation and change that y to f inverse. Now technically, you could stop after step 2. Once you've swapped your x's and your y's, you've found your inverse. But it isn't put back into function notation, so it doesn't really work very well or work very easily with future questions that might be asked. So it's always nice to continue the problem and solve for y and put it back into function notation if you're starting with function notation. So just try to be consistent. It is not necessary to go through these proofs like I just did on the last example each time you do this process. Once you swap your x's and y's, you can assume that you have correctly found the two inverses. So let's see some examples. So on this first problem, we're not actually given a formula for f of x. We're just given a list of ordered pairs. So the first thing we want to do before we jump into finding the inverse is you have to check whether or not it is one-to-one. And the way you check for that again is to make sure that you have unique x's and unique y's. So if I look at my x's, 1, 2, and 0, they're all unique. And if I look at my y's, 3, 4, and -3, they're all unique. So I have unique x's and y's, therefore it is one-to-one. So that means an inverse does exist, so we should be able to find it, and its notation would be f with this little -1, which means f inverse. And since there's not really a formula here, it's going to be fairly simple for me to find out what this inverse is by just physically swapping the x's and the y's. So 1, 3 becomes 3, 1, 2, 4 becomes 4, 2, and 0, -3 becomes -3, 0. And there's my inverse function. All right, now the next example here does have a formula. So we still want to check to make sure that it's one-to-one first before we jump into finding its inverse. So let's check to see if it's one-to-one by using that graphical horizontal line test. Because this function here is pretty easy to graph. It's just a line, because it's x to the first. We have a b of 1, so we have a y-intercept at 1, and we have a slope of 2, so we're going to go up 2 over 1. So here's my graph of g of x, and obviously that will pass my horizontal line test, so this is one-to-one because it passes the horizontal line test. So yes, it's one-to-one. Now once you know that it's one-to-one, you can go and find your inverse, and that's where we're going to go through these 4 steps right here. So step number 1. Step number 1 is to replace this function notation, this g of x, with y. So we're just swapping out that g of x with a y. Step 2, swap your x's and your y's to create that reverse or inverse. So this y becomes x, and this x becomes y. Step 3, solve for y. So I'm just going to subtract 1 to the other side, and I'm going to divide everything by 2, and you could create 3 different fractions here. I'm just going to make one great big fraction. So if I solve for y, I get this. And step 4 is just to use inverse notation. So since the name of my function was g of x, then my inverse function would be g inverse, and its rule would be this formula that we just came up with. And there's our inverse function. Okay? Let's try another one. So this one we have h of x equals square root of x minus 1. So first we want to check to see is it one-to-one or not, and I'm going to do that by graphing it. This is a square root graph, and we have a -1 inside of the parentheses, and so since it's inside of the parentheses or inside of the square root next to that x, that's a horizontal shift, and horizontal shifts go backwards from what you would expect, so a -1 means we're actually going to go to the right one. So instead of starting at the origin, this is going to start at 1, 0. And then the pattern for a square root graph is to go up 1 over 1, up 1 over 3, and it has this slow arcing shape to it. So does this graph pass the horizontal line test? Yes. Okay, so we know it's one-to-one, so we know it has an inverse. So here's how we find it. Step 1, change the h of x to a y. Step 2, swap your x and your y. Step 3, solve this for y. Now, if I want to get at that y, I need to get past that square root. And the only way to undo a square root is with a square, and we got to do it to both sides. So I'm going to square both sides. This becomes x squared. The square root and the square cancel out, giving me y minus 1, and I'm going to add 1 to both sides. So I get x squared plus 1 is equal to y. Step 4, change that y to the inverse notation. So since this was h of x originally, what we've just found is h inverse of x, and its formula is x squared plus 1. Now take a peek at the graph of this for a moment. X squared plus 1 is a parabola that's been shifted up 1 unit. Now does this graph right here, this parabola pointing up, look like it's the inverse of this square root graph? Do you remember that earlier problem we did with x squared? And when we reversed the correspondence, we got that sideways parabola. And in that example, we got both sides of the sideways parabola. And our square root here is just like the upper half of a sideways parabola. So something looks a little bit off here. So what I'm going to ask you to consider is your domains and your ranges. So look at this original graph up here. What's the domain of h? Because the graph starts at x equals to 1 and goes to the right, then its domain would be from 1 to infinity. What would be the range of h? Since it hits that x-axis at a height of 0 and goes up from there, its range would be 0 to infinity. Now what does that mean about our inverse function? Well, if you remember from an earlier comment I made about swapping x's and y's, domains and ranges also get swapped as well. So the domain of h inverse has to be the range of h. So the domain of h inverse should be 0 to infinity, and the range of h inverse comes from the domain of h. We're swapping these, so this would have to be from 1 to infinity. So let's revise our picture here. Instead of using the entire parabola, we're only supposed to use the part of the parabola that has a domain of 0 to infinity, which is just the positive x's. So actually, the only part of this parabola that we're allowed to use is this right half. So I'm going to go ahead and erase this other half. So because of the domains and ranges of the original function, we are not going to give just h of x, or h inverse of x equals x squared plus 1 as our whole answer. We need to include next to that what's the domain that we're using for that parabola and what would be the corresponding range, because otherwise you wouldn't have the correct inverse relationship. So it's always a good idea, especially when you're dealing with square roots and squares, to look at domains and ranges and always list out in your final answer what's the domain and what's the range that you're supposed to be using for that inverse function, to make sure that you're looking at just the right piece. Okay, we'll practice that some more. Let's go ahead and look at p of x equals to negative x squared plus 1. So this is a quadratic, so there's potentially some issues here. Let's first check to see that this is a one-to-one graph. So let's look at a graph. We know that x squared is a parabola that normally points up, so negative x squared would be a parabola that points down, and the plus 1 shifts this graph up 1 unit. So this is going to be a parabola that's been shifted up 1, but it's pointing down. So it's going to look something like this. Does that graph pass the horizontal line test? No, because it doesn't pass the horizontal line test for all these points down here. So that means no inverse function exists. Now occasionally in a problem like this, you can make an inverse function exist by restricting the domain of this original parabola. So I could have said that instead of using the entire parabola, let's just use half of it and let my domain be just the positives, for example. So if we had restricted our domain by forcing the graph to only be half the graph so it would pass that horizontal line test, then you could create an inverse function. But since this one didn't tell us to restrict the domain, then we can't do that, so no inverse function will exist. Okay, let's try another example here. This time for q of x, we have this big yucky fraction, and we want to find out what its inverse is. So first thing we're going to do is check to see if it's 1 to 1. And because this is a rational function, we are not probably that familiar with how to graph these, so I'm just going to use my calculator to help me out. So I'm going to pull up my calculator, and we're going to type in our function, making sure that we use parentheses around the numerator and around the denominator. And I'm just going to do a standard window and get a feel for what this looks like. Now, because it's a fraction, hopefully you know that when you're talking about fractional graphs or reciprocal graphs, they tend to have asymptotes. And this one does. It has a horizontal asymptote right through here at 4/3 actually. But what you want to look at when you're looking at this graph is, does it pass the horizontal line test? That's what we're trying to consider. So for all of these upper points, it obviously will pass. What you might worry about is right here in the middle. But if I draw this graph a little bit more for us on our picture, what's really going on is there's this invisible dashed line right through 4/3. So we do not overlap right there in the middle. So we don't have to worry about having repeating y's. So it does pass the horizontal line test, which means it is 1 to 1. Oops. Which is good news, because if it's 1 to 1, then that means it has to have an inverse function. So now we're going to find it. Okay? So step 1, change this q of x to a y. Step 2, swap x's and y's. Step 3, solve for y, and that's the hard part here. So what we want to do to solve this for y is try to get all the y's on one side and everything else on the other side. And because we have this fraction, probably the first thing we're going to want to do is clear out the fraction by multiplying both sides by the denominator. So that's what I'm going to do. Now on the left side, I want to take this x times this entire denominator. So use parentheses. We want x times parentheses 3y plus 2. On the right side, when I multiply by that denominator, it's going to cancel out my denominator, just leaving me with 4y minus 1. Let's go ahead and distribute our x across. And then what we want to look for here are our y terms. We have a y term here and a y term here. We need to get those together on the same side of the equation. So it doesn't matter which way you move them. I'm just going to go ahead and subtract this 3xy to both sides. The 2x will stay on the left, and it's by itself now. And I'm going to just rewrite this right-hand side, squeezing in that minus 3xy in the middle. And now we have this y term and this y term, but this negative 1 doesn't have a y, so it shouldn't be on the right-hand side. So I'm going to add it over to the left side. So we have 2x plus 1 equals 4y minus 3xy. Now this is a tricky step here to remember what to do. It's not hard to do, it's just hard to remember that that's what you need to do. Here what we're going to do is we're going to factor. If we have more than one y term, we can factor out that y from the right side. And if I factor it out, I'm going to be left with 4 minus 3x. And the left side stays 2x plus 1. Once you've factored out that y, to solve for it, you just divide by this factor that we're multiplying by. So I'm going to divide both sides by 4 minus 3x. So we end up with 2x plus 1 on the top, 4 minus 3x on the bottom, and that was what y was equal to, and I'm going to replace that y with my function notation, so this becomes q inverse of x. And there's our inverse function. So that one was just a little bit messy with the algebra. Okay, let's try another example here. This one is another quadratic. We've got j of x equals x squared plus x, and we want this for x is greater than or equal to 0. So let's go ahead and take a peek at this graph. Now you can graph this any way you like. It is quadratic, so you should be able to graph it by hand. I'm just going to pull up my calculator here real quick, and we'll graph it really quickly on here. We've got x squared plus x. So it's a simple parabola. It looks like it's got intercepts at -1 and 0, and it just dips below that x-axis slightly. So let me recopy that graph over here. So it looks kind of like this. It's got an x-intercept at -1 and 0. Now, because of this statement right here, the fact that we are being told to use x is greater than or equal to 0, then the only part of this graph that we get to use are these x's and y's over here. We don't get to use this part of the graph. So I'm actually going to take that part away. So my graph is just from here on up. So what's the domain of this black piece of the graph? Well, it's exactly this restriction that we were told to use. We wanted x's that are 0 or greater, so 0 to infinity. What would be the range then of this graph? Well, you can see that when x is 0, this function hits 0, so it goes through the origin. So the lowest that this graph goes is 0, so my range would be 0 to infinity as well, since it goes from 0 on up. So we're going to need to keep that in the back of our mind. That's the domain and the range of the original function j. And we're going to swap those to get our domain and our range of our inverse function. Is this graph with this domain restriction 1 to 1? Yes, because it will pass that horizontal line test. So yes, this is 1 to 1 because it passes the horizontal line test. And that only happened because we restricted our domain. If we had kept that full parabola, then we would have failed our horizontal line test. But because we're making this restriction, we do have an inverse, so we should be able to find it. So here's how we're going to find it. Step 1, replace that j of x with a y. Step 2, swap the x's and the y's. Step 3, solve for y. And this is where you might get stuck. This is tricky. It's similar to the last one in that there's going to be a lot of algebra involved, but it's not quite as nice as the last one, because in the last one, even though we had more than one y term over here, they were both linear y's, y to the first. And these two y's over here have different powers. So in order to attempt to solve this for y is going to require a special process that most students hate to do, called completing the square. So we're going to have to complete the square here to try and rewrite this in a factored notation so that we can try to get y by itself. So let me show you why this is going to work. First of all, leave x where it is, and what we're going to do on the right hand side is try to rewrite this in a factored notation. The leading coefficient of that y squared term is a 1, and that's good news. We need it to be a 1. If it is, then we're going to factor this into y plus exactly 1/2 of this middle coefficient, which is right now an implied 1. So half of 1 would be a half. Now let's see why this works. If you were to FOIL this out, you'd get your y squared back. You'd get a half y plus a half y, which is this 1y, but you'd also get a plus 1/4 on the end for your constant. So I'm missing a 1/4 on this right-hand side. If it were there, then these three terms would factor into this quantity squared. But I didn't have it. So what we're going to do is we're going to add in the 1/4 on the right-hand side, and then you have two options. You could either subtract the 1/4 right next to it, or in this kind of a situation, I like to just add that 1/4 to the left side as well. So I'm adding the same amount to both sides, which keeps the equation balanced. So that makes this x plus a 1/4 equals the quantity y plus a half squared. Now why does that help me? Why does that help me to solve it for y? Because then it just becomes an easy task of undoing this square, and we know how to undo a square. We take a square root. So we're going to take a square root of both sides. That'll cancel out the square on the right side, giving me a y plus a 1/2. But when you take a square root of both sides, you get two solutions, plus or minus. So we want plus or minus square root of x plus a fourth. Now to finish solving for y is easy, because all we have to do now is move that 1/2 over to the other side. And I like to write it in front of my plus or minus symbol. So we get something like this. Now this has two square roots, the plus case and the minus case. And you can imagine, hopefully in your mind here, that when you graph both of these, you're going to get sort of that sideways parabola going on. And we don't want both of them, because remember our original graph was only half of a parabola, so we want to make sure that we're only getting half of a sideways parabola when we look at the inverse. So we're going to need to decide which one of these to use for the correct domain and range to be maintained. So what I'm going to do is take a peek at my calculator again, and I'm going to go to my y equals, and I'm going to type in, let's just do the plus case first. So the plus case was negative 1/2 plus square root of x plus 1/4. Close the parentheses. And let's hit graph. And what we're trying to figure out here is which one is going to be the right graph. And how do you know which one is the right graph? You have to remember about your domains and your ranges. So let me go back to here for a moment. Remember that our domain and our range of the original function j was 0 to infinity for both. So that means the domain of j inverse also has to be 0 to infinity, and the range of j inverse also has to be 0 to infinity. So does this graph have a domain and range of 0 to infinity? Does it have positive range values? Yes. If you're not sure, let's take a look at the other case. Let's modify this, and instead of doing the plus square root, let's do the minus square root and graph that. And you can see here that this would be the bottom half of that sideways parabola, which means it would have a range of negative y values. And we want to have a range that's positive. So this minus case could not be the right solution. So what we want for our answer is the plus square root. So our j inverse of x needs to be the negative 1/2 plus square root of x plus 1/4. And not only am I going to put a box around that formula, I also need to put a box around my domain and my range restrictions over here, because they are important as well. They need to be maintained since we had a domain restriction on our original function. So include those in your answer. All right, let's take a peek at a couple of other examples here that are a little bit different. So this next example is very basic. All it tells us is that f of 3 is equal to 6. Based on that, what does f inverse of 6 have to be? And hopefully this is going to be fairly simple for you once you understand how inverses work, and you also might need to understand function notation a little bit. So if it tells us that f of 3 equals 6, that means that the function f takes 3 and sends it to 6. So the inverse function, because inverses swap x's and y's, that means f inverse has to take 6 and send it back to 3, which means that f inverse of 6 must equal 3. So it's a really simple question, because all we're doing is swapping x's and y's, but sometimes that function notation can get in the way and make it a little bit more difficult. Alright, we have something similar on the next example. This graph here is the graph of f of x. However, what we want to know about is f inverse. We want to know f inverse of 6. Okay? So that means we're trying to figure out where f inverse sends 6. Well, what we do know is that f, because it's the inverse of f inverse, has to take whatever I see over here, this question mark, and send it back to 6. So what we're going to do is we're going to use the graph of f to figure out where it hits 6. And remember, these are y values on this side. So we're looking for where this graph of f has a y value that's equal to 6. So what I like to do is I just draw a horizontal line through all the y's that are equal to 6, and I'm looking for where it's going to intersect, and you can see that it's hitting right at this point right here. What's the coordinates of this point? Well, if we drop this down here, looks like it's at 7, 6, which means that the function f takes 7 and sends it to 6, which means f inverse takes 6 and sends it to 7, which means f inverse of 6 must equal to 7. So again, it's just that inverse relationship, but understanding also how that function notation fits in. Okay, on the next example, we're going to graphically look at a function and its inverse. So let's start with f of x equals 2x minus 3, and let's go ahead and just graph that function first. It's a line because it has x to the first, and it has a b of negative 3, so it has a y value at negative 3, and it has a slope of 2, so I'm going to go up 2 over 1. And I'm going to draw several points here just so that I can get a fairly straight line when I'm graphing. So if I connect these dots, this is f of x. Now what we're going to do is we're going to graph f inverse of x, but I have to find f inverse of x first. So here's how we find the inverse function given a formula. Step 1, replace f of x with y. Step 2, swap the x's and the y's. Step 3, solve this for y. So I'm going to add 3 to both sides, and I'm going to divide everything by 2. And rewriting this, x over 2 is like a 1/2 x, just pushing that x to the side, plus a 3/2. And if you want to use function notation, this y was our f inverse. So our inverse function has as its formula 1/2 x plus 3/2. Now that we know its formula, let's graph it. This is also a line. It has a b of 3/2 or 1.5, so I'm going to put a dot right here. And then my slope is a half, so I'm going to go up 1 over 2, up 1 over 2, up 1 over 2, and so on. So my graph would look something like this. And there's f inverse. Now I want you to notice something graphically here that's going on. Imagine this diagonal line. This is the line y equals to x, right through the origin with a slope of 1. Notice that if you were to fold this piece of paper across that line, you would get the mirror image on the other side of that line. In other words, a function and its inverse are reflections of each other across the line y equals x. So that's a good thing to check for when you're graphing these, to make sure that you're looking at the right inverse function. Let's try that again on this next example. So our function f this time is negative square root of x minus 1. This is a square root graph. It's got a minus on the outside, which is a reflection over the x-axis because it's on the outside. So that's going to flip our graph upside down. And the minus 1 on the inside next to the x, that's a horizontal shift. And since it's a minus 1, we're actually going to go right 1. So we're going to take our square root graph, which normally goes through the origin, and we're going to shift it right 1, so it's going to start right here. And instead of going up 1 over 1, up 1 over 3, because of that reflection over the x-axis, we're going to go down 1, right 1, down 1, right 3. And so we get that same curving shape, but it's going downwards instead. Now this is a square root function, and we've done a couple of these by now that we should know that sometimes there's issues when you're talking about inverses of square roots and squares. So let's go ahead and take a minute to find out what the domain of this function is and the range of this function. So according to this graph, since my x starts at 1 and goes to the right, the domain of this square root is 1 to infinity. The range goes all the way down and goes no higher than 0. So the range would be minus infinity up to 0. So we're going to use that a little bit later on. Now that we have our graph done, let's go ahead and see if we can find out what the inverse function would be. So step 1 is to change f of x to y. Step 2 is to swap x's and y's. Step 3 is to solve for y. So I'm just going to go ahead and square both sides right away. So I get an x squared on the left side, and because I'm squaring, this negative on the outside is going to get squared away and disappear. Also, that's going to disappear as the square root. So we'll just get y minus 1, and I'm going to add 1 to both sides, and I get x squared plus 1 equals to y. If we label that f inverse of x, then our formula would be x squared plus 1. Now if I go to graph that, that's a parabola that's been shifted up 1 unit. So it would have a vertex at 1, and I'd go over 1 up 1 on both sides, over 1 up 3 on both sides. So I would have a parabola that looks like this. And remember we said in the earlier problem that there was this diagonal line, y equals to x, and our graph of our function, this red one, and the graph of its inverse, this blue one, were supposed to be reflections across this line. And obviously that's not happening. We've got too much blue going on and not enough red. So here's where that issue of domain and range come into play. So if the domain of the original function f was 1 to infinity, then the range of f inverse would have to be 1 to infinity. If the range of f was minus infinity to 0, then the domain of f inverse would have to be minus infinity to 0. So which part of this parabola has as its domain minus infinity up to 0? Domain is x's, so minus infinity to 0 are negative x's, and that means we want this left half of the parabola. So I'm going to erase this right half, and I'm going to include this domain and range restriction as part of my answer for my f inverse. And now after I remove it, my graph looks good. I do see that reflection across the line y equals x. So that's another way to check that you're doing it correctly. Draw in that line and make sure that you're looking at the correct reflection. So just to summarize that, the graph of a function f and the graph of its inverse, f inverse, are symmetric with respect to the line y equals x. So you should be able to draw that diagonal line and see that symmetry. Okay, the last example here is a graphical example, and all we're given is the graph of f of x. We're not given a formula or anything like that, and we want to draw its inverse graph. So there's lots of ways that you can do that. I'm going to go ahead and put in that diagonal line for reference, because we'll see that in use later on. And we're going to think about how we could come up with what the inverse should look like if all we know is this graph. Since we don't have a formula where we can swap x's and y's, one thing that we can do is swap coordinates of important key points on this graph. So let's take a look at some key points on the graph of this f right here. So I know this point right here, it has coordinates -4, -3. This point right here is -2, 0. And this point over here is 4, 2. So since we are looking for f inverse, and inverse is swap x's and y's, then this point right here would have to swap to -3, -4. This point becomes 0, -2, and this point becomes 2, 4. So let's plot those. -3, -4 would be right here. 0, -2 would be here, and 2, 4 would be up here. And each of these 3 dots was connected by line segments. So I'm just going to connect with my line segments, and there's my graph of f inverse. And you can see with that diagonal line that it does look symmetric across that line. So we obviously did it correctly. All right, good job. We just finished our lecture on inverse functions. Good luck.